Okay, now this problem right here, I basically did this in class, so I'm not going to do this one, but I am going to go on to this one. Okay. This is a little bit different than I thought we had. Okay, so use Fourier transforms to solve this equation. Okay, so I think this models this models a situation in which there is heat, like the system is actually losing heat. Okay, this models a situation in which the system is losing heat. It's losing heat if it's modeling heat. Let's just say it's modeling the heat equation, or the whatever. This models a situation in which it's almost like conservation. Well, conservation doesn't apply. It's where we have heat leaving the system at a rate that's proportional to the quantity of heat. Okay, so that's what this says here. Okay, and this isn't part of the question here, but notice if we were to try to do the same thing, and the same thing, meaning the same thing that we did up here. If we compute the integral, the t integral, we're going to get this integral right here. This part is going to be equal to 0, but we're going to be left with minus this gamma integral part here, and that part is not going to be equal to 0 unless the concentration of u is 0, which wouldn't make any sense. Okay, so what we should see then, so again, if we just kind of think through what's happening, so physically I didn't derive this for you, but physically what we should see then is going to be an exponential decay, because again, if we follow the same strategy we did up here and compute the t derivative, this is the amount of substance at time t. If we compute the t derivative of that and follow the same strategy, we're going to end up computing that integral just based on the fundamental theorem of calculus, assuming there's no flux even. If there is flux, this is different, but assuming there's no flux, that the integral corresponding to that term is going to be equal to 0. When I say no flux, I mean no flux in the boundary. So assuming that there's no stuff flowing in or out at the boundaries of an imaginary pipe, this is getting kind of confusing. So just in a couple seconds or whatever, I'll start actually solving this. The integral of this term is going to be equal to 0, and then we're just going to be left with the integral of this term. Gamma is positive. It should say, it doesn't have to be positive, but gamma is positive. If gamma is positive, the integral of u is non-negative, so overall the integral of the t derivative is going to be less than 0, which means the quantity of heat is decreasing. Okay, and actually we should get that there's going to be exponential decay here, because it's kind of like the increase is dependent on u here. Okay, so sorry about all of that. That was kind of some rambling about the physical relevance of this equation here. I haven't derived it in this class, and I don't think I will, but that is what it models. Okay, so let's use Fourier transforms to solve this. So taking Fourier transforms of both sides gives the following. On the left hand side, well, it's just going to be the I don't want to do it like this. The derivative of the Fourier transform, and on the right hand side it's going to be minus omega squared minus omega squared times the Fourier transform. I wrote omega up there, but here, just to make things consistent. Okay, and then minus gamma okay, whence, meaning, actually let me do one more line here just for the algebra's sake. Okay, so this is going to be minus omega squared plus gamma hat u of omega t. Let me just make sure this is what I want it to look like. Okay. Whence, meaning we're just going to solve this differential equation, or we know. Coincidence doesn't mean we're going to solve this differential equation, but from this we get the following. The Fourier transform of u is going to be equal to the Fourier transform of f, and then times e to the power of minus omega squared plus gamma t. And this, the truth is, this is a somewhat quick problem, but because of all of my rambling, I've made it even longer. E to the minus omega squared t, and then it's going to be e to the minus gamma t. Okay, because that's just a product. So let me see what this looks like. Okay, so notice as far as the Fourier transform variables are concerned, that's just omega and x. This is a constant. So, and we know what the inverse Fourier transform of this part is. We've already looked at that. Note that as far as omega and x are concerned, this is a constant. So the inverse Fourier transform, I can never remember if I'm supposed to capitalize a t or not. For people who are detail oriented, you probably get a little aggravated that I changed. Sorry. So the inverse Fourier transform of the above is, okay, so it's the solution, right? The inverse Fourier transform of this is the solution. U of x t equals, okay, so it's going to be e to the minus gamma t times the inverse Fourier transform of this part. Okay, and I think I'm just going to write that out to be a little explicit. So this is the inverse Fourier transform of this part here. Okay, but we know what that is. That's just the heat extension. So we're going to have this times 1 square root of 4 pi t, and then this is going to be the integral y going from minus infinity to positive infinity, and then we're going to have f of y, and then times the exponential part e to the minus x minus y squared, 4t, and this is going to be dy. Let's see, I might want to change some of that the way it's displayed. Man, you can barely see that minus sign. I think it's just because of the way this is displaying. Let me look if I do a defrac here. That's going to look a little bit better. Okay, I don't know. It's hard for me to know whether or not to have the defrac. I think I'm going to keep it like that. Okay, well, that's the answer right there.